to start. Hello everybody. Today is the second day of our conference, and to open the second day, Bartosz is starting to talk. I think that for most of us, Bartosz is not need to be introduced. He is well-known blogger, speaker, and today he talked for us about categories for C++ programmers. So, please, rock.
Thank you. Well, thank you for coming, even though the title of the talk is probably not something that is supposed to attract an audience of engineers and C++ programmers. Category theory is the most abstract branch of mathematics, right? And C++ is a reasonably low-level language, right? C++ is engineering at its best, right? Close to the machine, and category theory is mathematics at its best, really abstract, very, very high in the abstraction layer. So why have I decided to speak about category theory to C++ programmers? And there are many reasons. And the main reason is that category theory captures the essence of programming. Okay? We can program at many levels. And if I ask somebody, what is programming? Probably most engineers and C++ programming would say that this is about telling the computer what to do, right? We tell the computer what to do, how to move bytes from memory to the processor and back, and how to manipulate them and so on. Okay? But there's another view of programming, and it's related to the human side of programming, right? We are humans writing programs. So how do we decide what to tell the computer to do? Right? We are solving some problems. We are solving problems, and we are finding solutions to the problem, and we are translating it into the language that is understood by the computer. But what is problem solving? How do we humans approach problem solving? I mean, in our evolution, it was only a recent thing that we acquired these fantastic brains of ours, right? For millions and billions of years, there was nothing happening, and suddenly we get this brain, and we use this brain in the beginning to hunt animals, shoot arrows and stuff like this, and suddenly the same brain is supposed to solve problems in software engineering, right? So how do we approach problem solving? And I think there is one general way that we can describe problem solving that we have invented as humans, because of the limitations of our brain, not because of the limitation of computers or our tools. Because of the limitations of our brains have these small memory, the cache that's not very big. So when we are dealing with a huge problem, we have to split it into smaller parts, right? So we have to decompose bigger problems into smaller problems. And this is very human. This is what we do. We decompose bigger problems into smaller problems. And then we attack each problem separately, find a solution, and then once we have solutions to all the sub-problems, we recompose them. We recompose the solutions. So the essence of programming, I would insist, is composition. We decompose and then we recompose. So we have to learn something about composition. If we want to be good programmers, we have to understand composition. And who knows best about composing? Musicians, right? Composers. They are called composers. So let me show you an example. Okay? This is a composition by Johann Sebastian Bach, right? And I show you two versions of this composition. One is low level, and one is high level. Okay? Low level is just a sampling of sound. These are bytes, and they are displayed in this kind of waveformy way, right? And this is typical musical notation. Which one is easier to manipulate, and which one is easier to reason about? The high level one, right? I mean, notice in the high level description of the music, we have lots of these abstractions that we can deal with separately. We have split the problem into smaller parts. We know that there are things called notes, right? Sounds that are, and we know that they can be reproduced using, in this particular case, using violins, right? And if you notice that there are these little letters like E, A, B7, and so on, these are chords. They describe harmony. So there is harmony, there is melody, there are moving notes, there is the bass line. So musicians, when they write compositions, they use the higher level abstractions. And these higher level abstractions that they are using are easier to manipulate. They are easier to reason about or modify when necessary. That's this piece of music. I don't know if you can hear it, but that's... So this is what Bach was hearing in his ear, right? And the same thing can be represented in these two very different ways, but he chose to represent it this way. Now, if you're a rapper, probably you work with samples and you know how to manipulate these things. But it's a very different process of manipulating these things. So this is more like C++ programming at the lowest level, right? We're manipulating these samples. And we often do cut and paste even, right? Like rappers. And we would like to do something like this, wouldn't we? We would like to be like Bach. So how do we approach this problem as programmers, not as musicians? Okay, we cannot use musical notation to lift ourselves to higher levels of abstractions. We have to use mathematics. And there is one particular part of mathematics, category theory, that is about composition. This is exactly the part of mathematics that is about composition. And if programming is composition, then this is what we should be looking at. So a category theory is, in general, is not easy to learn. But the basic concepts of category theory are embarrassingly simple. Okay, so I will talk about these few embarrassingly simple concepts from category theory and explain them to you, and then I will show you how to use them in programming in kind of weird ways, the ways that you normally don't think about when you are programming. So what is this concept of category? These are two things. It's really simple. It's objects and arrows. Okay? So you have a bunch of objects, and in category theory, you don't ask about what these objects are. Okay? It's just abstract objects. You call them objects. You give them names like A, B, C, D, you know. And then you have arrows, and they just connect objects. So every arrow starts at some object and ends at another object. And you can have many arrows going between two objects. right? And they have names like F, G, H, and so on. And that's it. That's how you imagine a category. A bunch of objects, bunch of arrows between them, right? There are things that these arrows have to fulfill, and they are also very simple. Am I getting into, oops, sorry. As I said, composition is the essence of category theory and the essence of programming. So, how is composition defined in category theory? You have an arrow. Should I use the laser or just point it? From object A, represented here as piggy A, going to object B. And then you have another arrow that goes from object B to object C. These arrows are called composable because end of one is the beginning of the other. So every time you have composable arrows like these, and I call them F and G, right? There will be an arrow. There has to be an arrow that goes directly from A to C. Okay? That's the property of a category. That's part of the definition of the category. Every two morphisms, or arrows are sometimes called morphisms, so I'll use this interchangeably. Every two arrows that are composable will be composed. It's possible to compose them, and there is a composition of them. There's another arrow that's a composition. And this is what we do when we solve problems. We find an arrow from A to B. That's our sub-problem. We find an arrow from B to C. And then we compose it, and we get an arrow from A to C. That's the solution of our bigger problem. And of course, once we have this, we can then connect it to yet another object, C, and repeat this process, right? And when we start repeating this process, when we have, like, 3 arrows between 4 objects, right? Then the question is, okay, is the order in which I'm composing them, like, do I first compose F and G, and then compose this composed arrow with H? Or is it the same as if I compose G and H first, and then compose F on the left, right? So this is called associativity, right? Whether you can associate 3 things in 2 different ways. So do you need parentheses, right? Essentially, when you are composing more than 2 objects. And the answer is no. In category theory, composition has to be associative. So you don't need parentheses, okay? The grouping is not really necessary. Okay, so that's one thing, composition, that's associative. And then there's another thing. Every object has to have an identity arrow. So this is an arrow that goes from the object back to itself. Okay? There are these arrows that go back to the same object, the loops, right? And there is one loop for each object. There has to be in a category that's called an identity. And it has this property that if you compose it with any other arrow that either comes to this object or goes out of this object, you'll get this arrow back, right? It just acts like multiplying by 1 or like adding 0, right? It's an identity. It doesn't change anything. Composing with identity doesn't change anything. Okay? And I can immediately give you an example of a category, very, very simple category that you are, I'm sure you know and you've used all your life. And it's called a monoid. Maybe you didn't know that it was called monoid, but it is. So this is another embarrassingly simple concept. It's a category which has only one object. Okay? It has lots of arrows, but all these arrows have to start at this object and end at this object. So these are little loops, right? And since all these arrows start and end at the same object that are all composable, right? So you can compose any two arrows in this category. And there must be one arrow that is the identity arrow. So all these other arrows are not identities. They compose, they give you a new arrow. But if you compose one of these arrows with the identity arrow, you get back the same arrow. Okay? So the examples of these are very simple. Addition. So an arrow would be adding a number, adding 5. You compose it with adding 6, and you get an arrow corresponding to adding 11, right? Identity arrow is adding 0. Right? If you add 0, you don't change anything. So that's a monoid, addition of numbers with 0 as identity. Multiplication with 1 as identity. Right? Multiplying by 1 doesn't change anything. This is a very good one. String concatenation. In C++, it's a plus, right? You add strings. And an empty string is the identity. You concatenate an empty string, you get back the original string. What is funny about this one is it's very pure monoid. These actually have more structure. When you have string concatenation, there is nothing like an anti-string, negative string, or inverse string, right? You cannot take a hello world and say, now I'm concatenating anti-world to it, and I get back hello. No, you can't do that. Whereas with these you can, you have negative numbers, you have inverses, and so on. So they form actually more than monoids, they form groups. But this is like a pure monoid. But in programming, we have monoids all over the place, we just don't know. We don't call them that. But every time you have something like logging, gathering data, auditing, this is where you are using a monoid structure, because you always have, you're adding some information to a log, to something. You are appending it or concatenating with the previous information, right? And there always is something like, I don't have anything to add. Okay, so there has to be an identity element of logging, right? Something, I have nothing to add. Sorry. Right? So that's one example. But there's something even closer to our hearts as programmers, and that's the category of types and functions. Okay? And the funny thing is that this category of types and functions, it's actually almost enough to do programming, and in functional languages, that's what people do with types and functions. In C++, there is a little bit more noise than that, so it's harder to abstract this part of programming. But we do have types, right? It's a strongly typed language, and we do have functions. Okay, so let's talk about this category. And this category is actually called set, a category of sets, because at the simplest approximation, types are just sets. Every type is a set of values. Like you have type bool, right? It's a set of true and false. Ints, right? It's a set of integers, well, from 0 to whatever 32-bit maximum integer, right? 4 billion or so. So all these things are sets. If you have, a class, an object of a class, and so on, it's also it's an infinite set of possible objects, right? But it's a set. Now functions are just functions between these types. Every function, I'm taking the simplest possible function that takes just one argument and returns one value. So it takes an argument of some type and returns a value of some other type. So it is an arrow from one type to another, right? Can we compose these functions? Of course we can compose these functions. We do it all the time. We call one function, it returns some value, and with this value, we call another function. That's function composition, right? And in fact, this kind of procedural decomposition was the first serious technique for solving problems in programming, right? You decompose your bigger problem into a bunch of functions, and each function does a smaller thing, and then you compose them. The results of one function is going into another function. And this is like a tiny piece of code in C++ that composes two functions, f and g. Okay? It's not generic code, just shows you that you call f first with argument x, you get some y, and you call g with this y, and then you return this value. And this is a new function that is a composition of these two. Can you compose any two functions? Obviously, you can compose any two functions if they are composable, if the input of one matches the output of another, type-wise, right? So we have strong typing, and that's what we use. Is there an identity function? Well, in C++, we don't even have identity function in the library, which is too bad, because it's a complicated thing about how do you pass this? Do you pass it by value? Do you move it? Do you copy it? You know, and so on. Who's responsible for deallocating? But in functional languages, there's just one function called identity. Takes an argument and returns it back, the same argument. Okay. But if you just limit yourself to thinking, okay, let's just consider functions that are passing stuff by value for simplicity, then there is an identity of passing something by value and returning it immediately. Now, these functions that I'm talking about here are actually a special type of functions. They are called pure functions. They don't have any side effects. Mathematically, a function is just a mapping from one set to another set, and it's always returning the same thing. So what's the definition of a pure function? A pure function has no side effects, right? A mathematical function cannot have side effects. And it means two things. It means that when you call it with the same arguments, you will get the same results, always. Okay? So it doesn't have any memory, it doesn't have any access to some state, doesn't have static variables, doesn't use globals. So a pure function is really something that we strive to use in good programming. Like, we don't like global variables, we don't like static stuff, and so on. Sometimes we do use it, though. So this property is called referential transparency. And if you have a function that's pure, you can actually memorize it, which means if this function takes a long time to evaluate, maybe I'll just cache the value, right? And next time it's called with the same argument, I'll just look it up in the cache instead of evaluating this function again, like with the Fibonacci numbers, right? You calculate the same Fibonacci numbers 100th time. Why not just cache it? And another property of pure functions is that the dependencies in your code only come through composition, right? If you are calling two different functions and one of them is returning a value that you used to call the next one, then obviously you cannot invert them. You cannot first call the second function because you don't have the argument for it, right? So you have to call them in this order. First call this function, then call this function. So the dependencies between functions are totally explicit. You see, this function the result of this function is used in this function. So they are explicit dependencies. And that's very important, right? I mean, we know that compiler optimizers, they will try to rearrange your code. And they look at dependencies. And it's very hard in C++. Like if you call two functions, they don't have any, they are not composed or anything. They just calculate different things. You call them in a different order, and you might get a completely different result. right? Because they have side effects. And the order of side effects, which are invisible, right? Just by looking at functions, looking at your code, you would have to go into the implementation of these functions and find out everything about what they are doing, what other functions they are calling, and so on, in order to find out what the side effects are. And then you can decide, oh, actually, I can swap these two functions. Right? Now, in functional programming, when you only deal with pure functions, you can swap any two functions that are not composed. And composition is immediately visible. Okay, and at this point, I would expect half of the audience to just leave and say, okay, that's not how you can't program with pure functions, right? Programming is all about side effects, right? So, it's true, yes. So in order to keep you here, I will have to explain how you deal with side effects. But it's important that you start with something that's easy to understand and about which you can reason, like pure functions, and then build side effects on top of these things. So you can build up abstractions on top of other abstractions. So you start with pure functions, and then you talk about side effects. So instead of explaining you the general theory of side effects, in category theory, okay, I'll give you an example from programming. Okay, so let's solve this simple example that usually most C++ programmers would probably solve using side effects. And the example is auditing. So what you have is you have a sequence of functions that you compose, and for instance, you have these two functions. There is a function called getKey. You give it a password, and it returns a key. Okay, and another function, withdraw. You give it a key, and it gives you back money. Right? And you want to compose these two functions, right? So you start with a password, and you get money. Excellent scheme, right? And now you are saying, okay, but I have a new requirement. The new requirement is I want to have an audit trail. So every time any of these functions is called, I wanted to add something to an audit, to a log, right? So that I know what things happened, in what order. Okay? That's a side effect, right? So how do we solve this problem? How about using a global variable to store the audit trail, right? That's like the simplest solution that comes to mind. And of course, these functions that access global variables are not pure functions. So we are talking about side effects. Okay? So we would do something like this. We have a string audit. That's a global thing, right? And then in each of these functions, we would say, okay, access this global variable audit and concatenate something to it. Let's say, here you concatenate the password. Here you concatenate this string, withdrawing, and for simplicity, I'm just returning some fake numbers, because that's not the essence. The essence is what's happening. So this is not a good solution for many reasons, right? I mean, this solution doesn't scale very well, right? The maintenance of this solution is difficult. If you want to change the name of the auditing variable, then you would have to go through all this code and change it, right? It's not flexible. And if at some point you decide, oh, I want to actually log more information, so it's not just a string, maybe it's an object that has a string and a list of numbers, like timestamps or something. Then you go through all this code and you have to modify everything. So this is not the best solution. But there is a solution that's really pure. And it just says, okay, whatever you're accessing in your function, you have to pass it to this function and return from this function, right? And that's pure. So the next solution is you just modify these functions so that one of the arguments is this audit string, this log of messages from functions, right? And the return type is changed. So if it was int before, now it's a pair of int and string. If it was a double, then now it's a pair of double and string, right? And these functions return make pair, whatever was there before, plus they do this concatenation. They append password to audit, then they append withdrawing to audit, okay? So this is better, right? This is better solution because it's pure functions, right? They only depend on their arguments. They don't access any global state. They don't have any state. Every time you call them with the same arguments, you'll get the same result. The problem, though, is, well, they don't really memoize that well, okay? Because, like, if you look at this function password to key, you normally get the same key for the same password. But now if you want to memoize it when it takes two arguments, then you have to memoize it for all possible histories, right? So whatever audit string you were passed, if it's different this time, even though the password is the same, but the audit string is different, you cannot access your cache. You have to create a new cache entry for this, right? So your cache really explodes with all possible histories. So that's not good for memoizing. And the other thing is security, right? I mean, each of these functions has access to the complete log. So this function knows what password was entered there and can do stuff with it that, you know, we don't want to know. And also, each of these functions knows about things that maybe it shouldn't know. It knows about how to concatenate strings. You know, it knows how the log is implemented, the details of the implementation of the log. It knows that it's a string and that the strings are concatenated and has to do the concatenation by itself, and so on. It must know how to accumulate data. So now I want to show you a solution that's maybe not that obvious, and it kind of is a little bit outside of what we would normally think of. So first, let me notice that there is a certain thing that can be generalized easily. Okay, if I have functions of this type that I want to add auditing on top of these functions, right? Each of these functions takes some argument of some type and returns a value of some other type, right? Now, what I'm adding to it is I'm pairing the return type with a string. And I don't really care what the return type is, as long as I can pair it with string. Okay, so I have something like, okay, so in functional programming we call it lifting. You know, you give me a type, you give me a value of a type, and I'll give you a value of a new, more complex type, which is a pair of this and a string, right? So I'll okay, so this is was this what I'm showing? Okay, so now I have these functions that don't take the audit anymore, but they just return a pair. Okay, so they return a pair of, like the first function login was returning an int. Now it returns a pair of int and string. And it's only adding whatever it considers important. It doesn't have access to the whole audit tray. It's just doing its local thing. It's responsible for its local data, and it's not responsible for concatenation. It's just responsible for its own data. It has to create a pair, and it has a new return type, this lifted return type, right? But the problem is we don't know how to compose these functions now, right? because there's no way of passing a pair of int string to this function withdraw, because withdraw takes a key. Okay, so we don't know how to compose these functions. So let's go back a little bit and see how we can abstract this stuff. Okay, so so first of all, I can lift any type by making a pair containing this type and a string. So I do this data type. That's my embellished data type that contains a string on top of whatever there was previously. So there was some type previously. Now I'm embellishing it by adding a string. So my functions now, they return a writer of int. Okay? And we know it's just a pair of int and string, but I just want to make it clear that this is like this new embellished data type. Right? So we have these two functions and we want to compose them. How do we compose these functions? So I want to compose these two functions to create a new function called transact. So a transact function will just do these two things. It will log me in and then withdraw some money, right? So this compose function will take a password, because it needs a password to log in, and it will return the money plus the audit trail. Okay? But it will return the audit trail only of these two functions. So how do I do this? It's very simple. I call the first function with the password, right? It returns a pair of key and string. Then I call the second function. I extract the key. That's the first part of the pair, right? I get a new pair with money and string, right? And then I compose this by making a pair that returns the money from the second one, right? The first part of the second pair was the money I withdrew. It concatenates these two strings and puts them into a pair. So the accumulation here is done sort of, well, it doesn't look like it's between, but it's sort of between the calls, right? I'm just taking two functions and I'm saying I'm composing them in this funny way. And the accumulation of the log happens not inside these functions as it was before. They don't have access to the whole log. It happens outside. And I can take this, right, and abstract it. I can say, it doesn't really matter what functions I'm calling, right? I can do it for any two functions that return a pair or a writer, right? I can write generic code that does exactly this. And I will call this generic function compose. So what does compose do? It takes two functions. If the first function takes A and returns a writer of B, the second function takes a B and returns a writer of C. And when I compose them, I get a function that takes A, my original argument, and returns a writer of C, the final one, right? And internally, and this function just does composition. It has no idea that there are functions like login, withdraw, and so on, whatever other functions I come up with later. It just takes these two functions and glues them together, right? And this is the code you've seen in the previous slide. It just calls the first function, second function, and then concatenates the stuff and returns a pair, right? So it's composing two functions using a higher order function. So nowadays in C++, we have these higher order functions. We have, we can pass functions as arguments. We can return functions. We manipulate functions. And composition is this way of manipulating functions. And this is how I would implement my transact function now using compose, okay? Because transaction is nothing but just composition of two functions, right? It doesn't contain any other logic but this logic. Take this function, compose it with another function, right? And I'm using this compose, special compose, because I want to have an audit trail. And the audit trail is accumulated, as I say, between calls, because it's really in the glue in between. When I'm saying compose these two functions, I'm taking care of creating an audit trail from these two functions, of concatenating, right? Now this code has these explicit type annotations, which is kind of ugly, right? We would like to have something that actually infers the types. And we can do this in C++. In C++, I think in C++ 14 we can do this, right? We have these generalized lambdas with return type deduction, okay? That code, Eric Niebler gave me this code. So I asked him, you know, how do you do it so that you don't have to specify all the types? And this is the way to do this. You don't have to specify the types. When you are calling it, the compiler will figure out what types you're talking about. Okay, so that's a great thing. So this is our compose function. Okay? So now that we've done this, you know how to do this. Let's go back to where I started with, right? We said that the category theory, right? In category theory, we have functions and we have composition of functions. And here we also have functions and we have composition of functions. But this is a funny composition. That's not the one I talked before, right? Because the functions don't really match. Their arguments are simple types and their return types are these embellished types, these writers. So this is what we were dealing with before. We were dealing with this category where objects were data types, arrows were pure functions, and the composition was just, you know, result of one function is argument of the next function. So that was our category. What we have done right now is a different category, slightly different, okay? It's a category of embellished functions. The objects are still types, okay? The types like A, B, C, like integer, string, you know. But an arrow from A to B is not a function from type A to type B. It's a function from type A to the embellished type B. So it's some type that depends on B in a funny way. Okay? And in our case, this funny way of depending was creating a pair of this type and string, or creating a writer of A. Okay? So this is the way we are embellishing the results. And now we have to say, okay, so how do we compose these arrows, right? It's not as trivial as it was before. So we have one arrow that takes A into pair of B and string, and we have to compose it with another arrow that takes B, not a pair B string, just a B, and returns pair of C and string. And the composition should take A and return a pair, okay? And I have just defined this composition. I wrote code that does this, right? My compose meta function, the higher order function, it was doing just this. So, wait a moment. Do we have a category here that's different from our original category? And yes, we do. And this is called the Kleisli category in category theory. Right? It has compose, and it has identity. So what is an identity for this? It has to go like it has to be an arrow from the object to itself. So it has to be an arrow from A to A. But an arrow from A to A now is a function from A to a pair A string. Okay? So can we implement something like this? Yes, easily. We'll just return pair of the original value. So that's like the identity, the traditional identity function, and an empty string, right? An empty string doesn't change the audit trail, doesn't change the log. So pairing it with an empty string is an identity. Is this composition so this forms a different category. And what we have just done is that we turned controlling side effects into moving to a slightly different category, right? This auditing was our side effect, and now we were able to translate the problem into something that uses only pure functions, and yet it accumulates the trail, the audit trail. And the side effects were introduced. I mean, there are really no side effects. These are all pure functions, but it works as if we had the side effect of creating a trail. And the side effect was introduced through composition. And that's a funny way of looking at programming. We usually look at a program and we see functions. We see data returned by these functions. We pass it to other functions and so on. And here I'm saying that there is another dimension to programming that's kind of orthogonal to this, and that's that we can manipulate. We can say, okay, we are using these functions, but we are changing the way we compose functions. Okay, we have this new power of changing the way of composing functions. So we can now deal with this, solve some problems by saying, okay, we'll just move to these embellished functions, and we define a new way of composing them, and we'll glue them together using this composition that we'll put inside some kind of combinators, like this compose there, right? And this compose will do some work that I don't want these functions to do. I want this to be separated. I want this to be orthogonal. Now, does this approach generalize? Well, there are several generalizations of this. One, the very trivial generalization is that this writer data structure, it actually works for any monoid. It doesn't have to be strings, right? I mean, look back at how this is defined. So what happens to the second part of the string, right? All manipulation of the second part of the pair, which is the string, are done by concatenation here, this plus, and this little thingy here, empty string. Okay? Concatenation and empty string, that just generalizes naturally to a monoid. Concatenation is this associative operation. It has to be associative, because if this operation is not associative, then our composition will not be associative, right? And we want to have a category. So if we want composition to be associative, this plus here, or whatever we put in its place, has to be associative. And there has to be an empty log, right? It has to be an identity in our monoid. So it will work with any monoid. And that's great, because you have one more dimension in which you can modify your code without touching the rest. You say, okay, I'm changing the format of my log. Hey, I have to change compose and I have to change identity. That's all I have to do, right? I don't have to go through all my functions and modify them. They will still work, because all this concatenation of logs was done inside compose. It was not exposed to login or withdraw. So Now, I gave you a taste of this, and now you can go and study more stuff. The thing that I called embellishment, that's in category theory, it's called a functor. And you can implement functors in C++. This is not the functor that you are familiar with from C++, which is just a function object. It's a categorical functor, right? So there are lots of different embellishments that you can use here, and I gave you just one called writer. And now I can tell you the secret that this composition of functions, the funny composition of functions, embellished functions with a funny identity, that's really a monad. Okay, that's what in category theory is called monad, and in functional language it's called a monad. It's just a funny way of composing embellished functions so that they form a category. Now, are there any more interesting monads that I can use this construction with? Yes, lots. And I'll give you one example. And I'm really happy that Sean introduced futures, because futures, and I didn't write this new slide last night after listening to Sean. I already had it before, okay? But I thought I would have to explain much more. Now I don't have to explain much more. So functions that return future, that's our new embellishment, future of t. Give me any type, and I will embellish it by making it into a future. Like previously, I was pairing it with string. Now I'm turning into a future. This embellishment also produces a Kleisli category, and because it's a monad. The composition of these functions that return futures, okay, and you've seen this, it's done through this combinator then. So you call one function that returns a future, and you say, then when you're done with that, you call another function that returns a future, and so on. So you can combine them into long chains without ever having to block, right, to get. So that's the power of this composition. But now you know what's happening really in the abstract terms. You are creating a category based on future being a monad, okay? So we have new words to describe what we are doing. And there's an identity there. So it has to be a function that returns a kind of trivial future that's already, you don't block on it because it already contains a value. So you give it a value and say, give me a future with this value, but don't start a thread or anything. Just, you know, if I call get on this stuff, I'll just get immediately the value. And it's called make ready future. I don't know if it's coming into C++ 17 because there is still discussion about what to call this, you know, because maybe it can be generalized because there are many other instances of needing this kind of functionality. Now the problem with this, and it's a problem not only in C++ but even in Haskell, is that this is a lot of what in Haskell people call boilerplate code. Boilerplate code is just code that looks the same and you just have to repeat it everywhere, right? And in this case, it's this glue code, this calling the then here, then calling, you know, compose here, compose there. So like your all code will look like you're calling these functions that do the work, and then in between you put compose, 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 okay? That's kind of ugly. It obscures the real logic. You want to be able to program in terms of these functions, and the composition sort of should be implicit, or at least not as in your face. So people notice that, and the engineering solution to this is resumable functions in case of futures. Okay? So resumable functions do this composition of futures, of functions that return futures. Right? So here's an example. You have a function read that's asynchronous. It doesn't return the buffer. It returns a well, it takes a buffer, but it doesn't return immediately. It returns a future, right? It doesn't do its work. So this code is just copying one file into another file using a buffer. So it calls asynchronous read, asynchronous write in a loop, right? Now this code looks almost like sequential code, right? Except that it has these await keywords. Okay, and these await keywords, this is the point of insertion of our composition. This is where the stuff is actually chopped into pieces and composed using then. Okay, I'm not going to explain how this thing is implemented because this is described elsewhere in the C++ standard proposals, and it's also implemented in C#. But the main point is that composition of these embellished functions that return futures is almost hidden. It's just one little keyword here. And it really doesn't look like what you're doing is composing Kleisli categories, right? But it is. And it's different than the same code if you were to write in Haskell. Well, you wouldn't have a wait. You wouldn't have a loop because in Haskell you don't have a loop. You would have recursion, right? But in C++ you can do it with loops. And it's a very powerful mechanism. And it's usually described at very low levels, saying, okay, these are coroutines, and we implement it using a state machine and gotos, and there's some state that's remembered in a static variable, and then when you call it next time, it does a goto to a place where the last await was, and so on. So once you start talking about implementation, you lose this abstract idea that this is all really about composition in this future monad. Okay? And the high-level code like this is hiding the glue that's part of the monad. And I think what is being lost here in all this engineering talk about coroutines, state machines, and so on, is that how general and powerful this idea is. Because here's a different code, okay, that does completely different stuff. It calculates, Fibonacci numbers, okay? It's not efficient, it's just an example, okay? But it calculates them on demand. So it creates a generator of Fibonacci numbers, right? And instead of await, it has this underscore, because this is a proposal, experimental, yield value, okay? And yield value is sort of like our await, and this is sort of like resumable function, except that it's a different monad. It's the other monad was a continuation monad, and this monad is the list monad. And actually, this kind of code, when combined with the range library that's been proposed by Eric Niebler, this would be great. This would let you write very simple code to do really complex things using the same mechanism. But why do we have to have separately resumable functions and separately generators implemented maybe using different way? This is the same pattern. This is the same monadic pattern. So there is this great opportunity now in C++, which I am afraid will be missed, like many other opportunities for great generalizations were missed in C++, and that's to introduce monads and to introduce this kind of monadic pattern that's general rather than solving one problem at a time. And the same pattern can be used, so as I call it the grand unification, to control all kinds of side effects. Futures are one example. Ranges is another example. Exceptions actually form the same pattern. This is the maybe monad or optional monad actually can be used to implement exceptions. Continuation monad. And all kinds of user-defined monads. Okay? This is the real power that could be put into C++ if we start thinking in more abstract terms, if we start using this more abstract understanding of what's going on in programming, when we start thinking about category theory. Okay? Thank you.
Sorry.
Sorry.
So
yeah.
all the discussions and questions.
You can catch me.